Welcome and thanks for attending today's Ask CTE Contributors webinar on drilling with high pressure coolant. I'm Timothy Spaeth, the digital media producer with Cutting Tool Engineering, and I'll be serving as the host and moderator for this 1-hour webinar. Today's webinar is an extension of the feature article, A Fluid Choice. Published in this month's issue of Cutting Tool Engineering, this article addresses how water miscible fluid and neat oil stack up when deep hole drilling with high pressure coolant, and was authored by Alan Richter, CTE Editor-at-Large. I would like to introduce our two presenters. We have here with us Tim Schneider and Brett Reynolds. Tim Schneider is the Vice President of ATS Systems. He is a seasoned professional in the machine tool industry. His journey in the industry began in 2001. Since then, he has become a specialist in the design and application of high-pressure coolant systems and was asked to contribute to the article from CTE on proper deep hole drilling processes. Also presenting today is Brett Reynolds, a certified metalworking fluid specialist accredited by the Society of Tribologists and Lubrication Engineers. He has been with Blazer Swiss Lube for 20 years, and his current position is in customer service as a senior application engineer. To start off, Tim Schneider will go into more detail about how high-pressure coolant for deep hole drilling enhances precision and efficiency. And with that, Tim, if you would like to share your screen, we could get started.
See if we can do that. Thanks, everybody, for joining. We'll get right to this and make sure it's as painless as possible. I'm going to go through our agenda today. We've already done the introductions, so we won't waste our time on that. Just a brief overview of the deep hole drilling process, importance of high pressure coolant systems, case studies, examples, orifice sizing and machine requirements, coolant concentration requirements, high pressure applications, and then your Q&A to follow. In any case, for your recommended deep hole process, drilling process, you want to start with the longest stock drill that you have for your hole diameter and pound that through it to the highest penetration rates you can. Again, key thing here is making sure all your drills are indicated. Next, you just go to step 2, moving on to the longest drill, your deep hole drill to finish the hole, either twist or gun drill. What we tell you is to start the coolant flow before with no rotation, get the tip of the drill in. That creates like a bushing for that drill so you don't get any tool whip. And after you get the tip into there, you with the coolant flowing already, then you start the rotation and continue the process. Key indicator here is that both drills must have the same point geometry. And other key indicators or things that you need to look for is if you have a cross hole, you want to make sure on your breakthrough that you reduce speed just before the breakthrough up to 50%. Because once you hit a breakthrough hole, you no longer have a pressurized hole, so that can create damages to your drill margins and everything. Outside of that, that's really as technical as it gets to the application of the deep hole drilling process. It's about making sure that your drills are indicated, have the same point geometry, and that you are following that coolant on without rotation process to make sure you don't nick your margins going into the hole. As far as the other things that we want to go over here, and certainly asking questions, the hole sizes and such. I saw some questions there that we'll address later, but we'll talk about the importance of high pressure with your systems and what that means. High pressure applications in your operations will give you faster cutting, longer tool life, and control your chips. Properly applied high pressure coolant addresses heat damage, chip damage, and poor lubricity. Gets you the proper coolant force to the chip tool interface, allows tools to wear instead of fail from heat damage, aids in chip breakage. This is very important. A lot of people think when they're buying high pressure that they are getting high pressure to break chips, and high pressure does not break chips. What it does is just aids in that process. You still have to have the correct speeds, feeds, and chip breaker geometries on your inserts that will allow the formation of the chips correctly, and then the proper volume and pressure from the coolant just rapidly evacuates the chips, which provides you the increased tool life and the faster speeds and feeds. The key, I call it the 5 Ps. That's your key to the successful application of high pressure coolant. What that requires is proper volume, proper pressure, proper orifice size, proper coolant concentration, and proper filtration. If you're missing any one of these, and you're going to diminish the effectiveness of your high pressure application and can possibly have negative results. High pressure case studies, just to give you some examples of the power of the high pressure. Here's a case of tool life in titanium. Customer was doing 90 surface feet, 2.65 inches a minute, 2 PECs, and getting 100 holes per drill. After we applied high pressure, it's going 116 surface feet, 7.9 inches a minute, and got 1,680 holes per drill. So you can see the power of performance there. Another tool life example in single point turning, you're getting 18 minutes of cut time from the insert. Once you applied high pressure, you got 10 times that, or 187 minutes. And obviously you can see the difference in the chip formations as well, and what that can mean to your operation. That was also an exotic in 718 Inconel. Another sample of chip control. In the picture here, you can see how individuals are getting the long stringer chips wrapped around their machinery. That was low pressure operations. Adding high pressure, you can see the nice chip formation you got. Fun fact about this one is that was actually a customer that said he needed 3,000 PSI. And when we did 3,000 PSI, we actually got the same chip formation. So we were able to convince him that he just needed to stick at the 1,000, which is a obviously lower cost and more safe unit to work with. Other samples of chip control showing the differences in that chip formation. And I'm sure anybody that's got the experience in shop knows what that means to them. Here's another sample of increased speed drilling 4320 material. Went from 47 inches a minute to 140 inches a minute. Well, the improvement of part finishes is another huge factor for you. This is a close-up picture of running mill through aluminum, and all the residue you get there with low pressure, and how that on the right or on the left, how that looks with high pressure applied, how much cleaner your part finish is. Talking about what's really critical in high pressure operations, be it any of the operations, deep hole drilling or anything, is your orifice size. Your drills should have. All the manufacturers now are doing a really good job about having drills with the proper orifice size to pass the proper volume for the tool diameter. When you're talking about single point operations and things, it's about having proper orifice size and aiming. If this red square indicates where you want that coolant to hit, you need to have that focused energy stream of coolant on there, and you become 99% effective in dissipating the heat and helping with the chip evacuation. The lower shows you a sample of the standard low energy or low pressure operations, and as you can see, you're only about 2% effective. Most of your coolant is not even hitting the target, and it boils away before it actually gets there. So it's almost useless to have it there anyway. Here we show some samples of properly directed coolant to the cut zone. You're talking about you want to have the recommended is a 10-degree angle coming in. Again, these slides were originally designed way before tooling manufacturers were making coolant through tools. Now they do a great job. You pretty much buy them off the shelf and be ready to go. You want to have some checks and balances to make sure that these rules apply, But if you're getting that coolant directly, accurately put in there, you're going to get the results you're looking for. Again, here's a sample. In the low pressure operations, you get a long shear zone, which creates the long stringer chips. Down below, we're showing that directive force of the coolant sent to the chip tool interface, which gives you the shorter shear zone and gives you a quicker curling chip, which breaks more easily. A cooled chip. Just some samples of a good orifice or nozzle types that you can use, and showing on the right picture here, showing about how to get it directed as close as you can to the tool. This would obviously be a tool that's not coolant through, so you're lining it up from the tool station, getting it as close as you can to the insert. So there are some cheaper ways to address tooling if you need to, and those are things you could always call and talk about. Volume and orifice data, talking about in drilling, milling, turning, and grinding, you got different volume requirements. Drilling standard is 9 GPM per 1 inch of tool diameter, or 36 liters, 25 millimeter. Your milling rule of thumb is 1 GPM per tooth. Turning is half a gallon per horsepower. And grinding is usually 9 gallons per inch of wheel diameter. Just to show the importance of orifice sizes, when you look here in point number 1, your standard size of systems out there around 8, 9, 10 GPM depending. And what that requires is a maximum of 100 thousandths orifice in order to maintain the 70 bar 1000 psi pressure. 1000 psi being what I call probably the golden number in there. There are some situations where you need higher pressure, and that's typically with the delivery of oil. Water soluble, you're generally good enough always at 1000. You only go up higher on pressure when you need to get more volume through the orifice. But again, the measure for orifice size is the capacity of the system. What a 9 GPM system, your maximum is going to be 1000 GPM. Am I still on there, Tim?
Yep, you're still on.
Okay, I beeped again. So, and what I want you to notice here is when you basically increase the volume of the system, it doesn't double the size of the orifice. A 16 GPM system is still only 140 thousandths. And this is where people get into a lot of trouble in the high pressure application, is they don't restrict the orifice, and then they call and say your system doesn't work because you're not getting pressure. Well, the pressure is directly related to the volume supplied versus the tooling orifice, and you got to make sure that those are all in sync. As far as machine tool requirements, making sure that the tool is capable of handling the required pressure, that the machine has M codes, and M codes required for multiple M codes required if you're looking to do multiple pressure operations. The systems are capable, variable volume systems are capable of having multiple pressure settings, but I can like to try and discourage that because of the complexity of it and the fact that most organizations, their machine programmers don't program in multiple pressures anyway. So, and overall, your 1000 psi is your best pressure in almost all circumstances. Again, just talking about lathes and volume size required for that. That works, except when it doesn't. Sometimes you have a higher horsepower lathe, but the tank capacity is small, so you've got to be concerned about that as well. And make sure you manage it with orifices instead. But those are something we can certainly work with you to do. I'm not going to go through that. Talking about different concentration levels for different tools. Single point is 5%, drills are 8%, reamers 10, and taps 12. Our best overall recommendation is 8%. That's going to take you through your tool ranges without starving taps and not overdoing single points. And what that means is it'll keep you in a good range for coolants to work with high pressure without being too rich and potentially causing foaming. Last thing I can show you here is high pressure applications and what it's good for. Basically, high pressure can be adapted to any of the applications: drilling, turning, milling, grinding, caging, any material: aluminum, steel, brass, titanium, or plastics. Any industry can benefit from it in all the different market sectors. And that's pretty much what I have for you today. I appreciate your time and looking into it.
Thank you, Tim. If you would kindly stop sharing your screen,
Yeah.
and we will move on. All right, let's see. We will now move on to Brett Reynolds, who will discuss gun drilling and fluid selection.
Thank you, Tim. Appreciate it. Thank you for attending this webinar. We're going to talk to you a little bit about the types of metalworking fluids that are typically used in gun drilling. So what we're going to kind of cover a bird's eye view of gun drilling and deep hole drilling. For those who may not be familiar with it, we're also going to talk about the different types of metalworking fluid requirements, the fluid delivery, other considerations you may want to take into account, and also some common issues that you might see in gun drilling, as well as a case study for you to take a look at. So what is deep hole drilling? Deep hole drilling is a hole depth with at least 5 times greater than the diameter of the drill itself. There are different types of drills used in deep hole making: twist drills, single lip gun drills, BTA, STS single tube system drills, and ejector type drills. Twist drills is your parabolic flute, really long length drills. These are great for getting chips back out of the hole. We do recommend that you don't go exceed 50 to 1 ratio on the hole depth, because these are unsupported drills and you might get a lot of hole deflection if you go much longer than 50 to 1. Gun drilling, however, that's more typical of your dedicated gun drill machine. So you can see on the schematic here, it's quite a different process. It's a horizontal machine, which has a supported drill, which is fed copious amounts of fluid through the drill to evacuate the chips out of the hole. And you can actually go up to anywhere from 300 to 1, even up to 400 to 1 depth to diameter ratio with these types of machines. So typical drill diameter ratios: 5 to 1 are your common twist drills, 10 to 1 high performance twist drills, 20 to 1 special deep hole drills with through tool coolant. Usually when you get up to over 50 to 1 and you're going to start moving into like the 100 to 1, it's your dedicated gun drill machine. So 200 to 1, very high performance gun drilling machine. And then if you go up to 400 to 1, you're talking about proprietary equipment design. And, usually it's a very specialized field when you start getting into that size of drills. The gun drill types, you have your typical conventional single lip gun drills. These are a solid rod that has a hole through it with a carbide tip. These are fed fluid through the internal and through the tool, and the chips are evacuated down the flute and out of the hole. Your BTA or STS, which is BTA stands for Boring and Trepanning Association, STS single tube system. This is a cutting tool that's a tube. Basically, the fluid is pumped around the outside of the cutting tool, and the chips are removed through the center of the tube. There's also an ejector drill, which is a dual tube system, where oil is pumped through the outside tube, and the chips are removed through the internal tube. So these are the different types of gun drills that you'll see. So when we talk about metalworking fluid requirements for gun drilling, gun drilling is a very demanding application, so it requires fluids which deliver high levels of lubricity. Traditionally and historically, neat oils, or oils which are not mixed with water, that's what we mean by neat. If you order a whiskey neat, it means without oil. Same nomenclature is utilized in metalworking fluids. Typically, these have always been used in your traditional gun drills, but now we're starting to see people asking for water miscible coolants in the same type for these type of machines. And there's reasons and benefits to those type of fluids being utilized, and we'll cover those as we go. Um, Water miscible fluids, you have the quenching capabilities of water, and when you have that, you can go faster. Okay, so neat oil really brings the absolute lubricity that you can get, the highest lubricity at the cutting edge, but you're limited by how fast you can go. So if you go too fast, you can take the risk of setting the oil on fire, and then you have a really bad problem on your hands. With coolants, you can go faster because you have the quenching capabilities of water. Um, the drawback with coolants can be that you're not going to get to as high lubricity levels with a coolant than you will with a neat oil. Sorry about that. This thing has it likes to kick people off for some reason. So you do have the ability to go faster, and with coolant, and also the oil blows. I mean, the coolant blows off a lot easier than a neat oil would. Um, Neat oil, you just get the best tool performance, cutting performance, best lubricity with that type of metalworking fluid. So metalworking fluids basically have additives. So the oil really provides a certain level of lubricity, but it's also a carrier of the additives, which actually protect the cutting tool up to very high cutting temperatures, up to 1200 degrees Fahrenheit. So we utilize what we call extreme pressure additives in these metalworking fluids, and these are activated under heat and pressure, and they release and form typically a protective coating on the tool itself. So typical EP additives we see in metalworking fluids are sulfur, chlorine, phosphorus. When these are activated under heat and pressure, you form a metal sulfide or a metal chloride or a metal phosphide type coating on the cutting tool, which has a very high level of lubricity, and it keeps the tool from getting the built up edge or the chip weld to the actual cutting edge. Sometimes in metalworking fluids, you'll see a combination of these in a particular formulation. It's very, very common. So also the base oil that we utilize in cutting fluids offers different types of properties. So, we have what we call ester-based base oils, which these are vegetable derived from natural like plant oils. These can be converted to synthetic esters, which are basically you're reacting the ester with an acid and an alcohol, and you're changing the molecule structure. It's a method called transesterification. Basically, esters are not only are they green substances, they're naturally and readily biodegradable. They also have very unique properties to them, which provide a very good which we call basically a polar molecule. So it has a negative and positive charge to it, and so it has a very uniform boundary layer of lubrication that basically has a great affinity for the metalwork piece. So you get a very dense, uniform film, which delivers the additives more effectively to the cutting tool. They also have a very high viscosity index, which means that they do not get extremely thick when they get cold, nor do they get extremely thin when they get hot. Especially when you compare these to typical paraffinic-based oils. Another unique oil that's being utilized in metalworking fluids today is gas to liquid technology. So gas to liquid technology is basically you take natural gas and you basically transform it through a unique refinery method. And what you get is basically a very, very pure synthetic hydrocarbon, which has very high levels of, of viscosity index, talking about how, does it get thick when it gets cold, does it get thin when it gets hot, and it offers a lot of the benefits that are traditionally associated with polyalpha olefins, which are typical full synthetic oils, without the high cost of the polyalpha olefin. So they also offer very fast release, air release properties, which is very advantageous in metalworking fluids. So these are being utilized more and more in the metalworking fluid industry. So fluid delivery. So this is really critical. If you just have coolant just shooting down onto the tool, maybe you're hitting the tool higher up, and you're hoping that the fluid flows down through the flutes to the cutting edge, or you're not really getting fluid into the hole. You're really machining with coolant. So you really need to be able to deliver the coolant to the cutting edge. Typically, that's best done with coolant-fed drills. So it's really important that the fluid reaches the drill tip to get the optimal cutting performance. Okay. Also, adequate coolant pressure, as Tim talked about, will certainly ensure that the chips are evacuated quickly away from the cutting zone, and provides high levels of cooling to that cutting edge. Other considerations is good filtration. When you cut material, you're heating that material and you're changing it metallurgically. So you don't want to be recutting chips. So those chips are harder than the virgin material that you're actually cutting. So you want to make sure you have good filtration to filter out those chips, so you're not spraying chips that are in the submicron range or microns range onto the cutting tool. So good filtration, especially if you're using neat oil. You want to have a fluid chiller on the machine to keep the heat regulated. Oil does not like to release heat very fast. It kind of holds on to it. So that means that when you utilize neat oil, as it gets pumped through the system, the pumps generate calories of energy, which is put back into the oil, and it continues to build up to a very high level, and the oil can get very hot. When you have high levels of heat, especially the neat oil, it can rapidly oxidize that fluid. So you want to make sure you can control the temperature range of the fluid. So you may have to have a chiller installed on the machine itself. Periodic maintenance. This not so much applies to neat oils, but more applies to water miscible coolants. Those need to make sure that the concentration is in the proper range that's recommended for the application. Also, there's different properties that we check on those fluids, such as pH range, and and we also test for different levels of microorganisms to make sure that they aren't present in the fluid. Also, want to make sure you work with a manufacturer, cutting fluid supplier that has lab testing capabilities, so you can send in the fluid periodically to have it checked, make sure everything is where it's supposed to be, and good technical know-how and customer support. Common issues you see with gun drilling. I'm not going to go really into this chart a lot, but you can see there's quite a range. But what's really interesting here, if you look at all the different types of tool problems that you can have, a lot of them, just being the wrong product being spec'd in, can really be the main driver of a lot of the problems. So it's really important that you work with a supplier that's knowledgeable on gun drilling, so they can help you, because invariably you're going to run into some issues, and it's good to have a partner you can work with that can help you work through those issues. And here's a case study. This is on one of our products against a competitor oil of the same viscosity range. So this customer manufactures parts for the mining industry. The component is a pin, basically. The material is alloy steel. We're drilling in gun drilling, 7.5 millimeter gun drill. The machine is, I don't know what machine manufacturer that model number is, but it's a gun drilling machine. The drill length is 450 millimeters. So with the competitor oil, The feed rate was at 25 millimeters per minute. With the our Blaser Mill 10 DM, which is an oil that is designed for gun drilling, DM meaning deep hole machining, we was able to achieve 42.5 millimeters per minute. The RPM we was able to increase from 1800 to 2150. Tool life by number of parts. With the competitor oil, we're getting about 70 parts per drill. We went up to 85 parts per drill, but the real benefit was in the cycle time reduction, which was 1,140 seconds down to 630 seconds. So which basically translates into overall machining costs were reduced by 45%, and the tooling cost per component was reduced down to 18%. The faster you can get parts off the machine, the higher the level of productivity you get, the more throughput you get through the machine, the more benefit you get from a standpoint of reducing costs. Tool life is nice. We certainly want to extend the life of the tools, but if you can get parts off the machine faster, you're going to make a lot more money. And that is all I have. So I thank you for your attention, and turn it back over to you, Tim.
Thank you, Brett. Thank you for that amazing presentation. Let me adjust the screen. So now we're going to open up the floor for questions. So to the audience, I'm going to start the Q&A now. And if you have any questions, you could either enter them into the chat or the Q&A section that should appear next to the chat. But in the meantime, we have some pre questions that were submitted prior to the webinar. So if you guys both want to offer your 2 cents to all these questions, take it away.
Go ahead, Tim.
Okay, so thanks, Brett. So on the first one, what concentration level are you running at? Well, I think we touched on that a little bit. That's obviously concentration is not an issue for the oils, but for your water-based coolants, you're looking at again. Our standard would be 8%. Is what you want to run for your drills. Potentially 10% if you're going really, really deep, but 8% overall without having to worry about changing your concentration in your standard general operation. Again, PSI, 1,000 PSI is your best overall pressure. If you're expanding into the oil, you may need to look at going to a little higher pressure than that. But as far as the deep hole drilling for 1/16 diameter, all the same principles apply. I don't think there's anything special. The biggest key to those is making sure that your tool holding is proper so you have no leaks. So all your volume and pressure is getting through the flutes of the drill. That's the most critical part there. And then following those points for the application of the deep hole drilling. And lower viscosity oils for smaller coolants. Again, the viscosity obviously has to do more with your lubricity, but also the thickness. So smaller drills, you want lower viscosities. But again, that can be adjusted based on the machine, the pressures used to push that oil through. But obviously, the lower the viscosity, the less propensity it has to hold the heat as well. But lower pressure would also be a consideration in that. Why oil? Well, again, Brett touched on that, and I'll let him actually say that more because of the lubricative properties of oil versus water. Probably be the main advantage there. But Brett, you can take over that one.
Yeah, sure. I'll go back over the same questions as well because there's some stuff that we can add from the standpoint of metalworking fluid. So, for what concentration level are you running at? Well, that really dictates the materials that you're doing, the application and operation that you're doing. So, it can range anywhere from, like Tim says, up 8%, sometimes up to 15%. It really depends on the material, how tough it is, the additive packages that you're using in the metalworking fluids. And, so really you need to talk to your metalworking fluid supplier. That would be the best answer for that. What does a PSI recommend for gun drilling parts? So yeah, I agree with Tim. 1,000 PSI tends to be the sweet spot, especially for water miscible coolants. Neat oils, you may have to go up to 2,000 PSI. It really depends on the size of the drill and the flow rate through the machine, as well as the holes that are in the drill itself. If you're dealing with extremely small drills with really small orifice sizes, you're going to have to go to a really thin viscosity oil to get that to actually to work. Um, for some reason, my screen has gone blank there. It's like a
Yeah, we can hear you. I just can't see you.
Here,
maybe that's the
no,
reason why my thing just kicked me off.
oh,
Okay.
dead.
There you go.
There we go. All right. So, deep hole drilling, 16th diameter, really close run out. What do I need to do to make this work? So, with a really small drill like that, if you're using neat oil, the pressure requirements are going to be rather high. If you look at on Sterling Drills, which is Eldorado Gun Drills, if you look on their website, they're recommending for a 16th diameter drill at 2,000 psi for neat oil. So you may not be able to have that capability on your machine. So the best advice we can give you is to make sure you have a good pilot hole drilled, and so you have good centering properties, and make sure that you have good coolant flow. If you get those things done correctly, you should have pretty good, possibly making pretty straight holes. So, but there is, certain applications where you may not be able to achieve, the optimum, cutting parameters for that drill just because your machine doesn't have the capability. So that, things like that happen. Lower viscosity oils for small through coolant through fed drills. Yeah, typically, thinner viscosity oils are used for smaller cutting tools. There's not really a cutoff point per se on where we would say, oh, you want to use a 10 centistoke viscosity oil versus a 20 centistoke viscosity oil. But your fluid manufacturer can certainly help you with that. My rule of thumb is if it's like 3/4 of an inch and higher drill size, typically you're going to benefit from a thicker oil. So 20 centistokes would be beneficial versus a oil with only 8 or 10 centistokes. So those are things you want to talk to your fluid supplier about. And then why oil versus coolant and deep hole drilling? Is it performance versus convenience? Yeah, it's a little bit of both. So with oil, they tend to be more messy. From a convenience standpoint, that's not very convenient for a lot of folks. So coolant in that regard is pretty nice because it just blows right off. A lot of the thinner viscosity neat oils blow off pretty nice now, and so that may not be as big of a problem if you're dealing with a real thin oil. But with a thicker oil, sure, it can be a little more messy. Certainly if you need the most performance you can get, neat oil is going to be a little more of a benefit than you will with coolant as far as the overall drill performance, the whole finishes, and basically how long the cutting tool and the drill is going to last. So, but if you need higher throughput, certainly water miscible coolants are going to they're going to deliver that because you're dealing with an oil water emulsion, which basically get a synergistic effect of not only the oil but the quenching capabilities of the water. So so there's give and take with any fluid. There's no such thing as an ideal metalworking fluid. There's give and take with everything, and so you have to take the good with the bad, regardless, of what you're doing. So, and that's all really I have to add on those questions.
Thank you for answering those questions. And if you, Brett or Tim, have any anything else, additional information you would like to share, you can. Oh, yeah, and we did just get a question, so I will go ahead and read that. How many metalworking fluid types in the industry? Wait, hold on. I need to pull my computer a little closer. Okay, this is a question for both the speakers. How many metalworking fluid types in industry? Of course, is too many. I mean, the real question is, should oil type change when material change? For example, steel to aluminum or titanium or Inconel. And I believe viscosity is also has too much effect on tool life as pressure does. Um, I don't
Uh,
know. Did you guys understand that?
Vaguely, I think
I think
that
so.
um, changing fluid types based on material types. Obviously, the metalworking fluid companies work very hard to have their fluid be able to be used in multiple materials, but there are limitations, obviously, and Brett, I'm sure, will be able to talk more specifically about that. But um, you know, uh, that's a challenge of the machine shop itself. How many different materials are you working with? If you're an aluminum shop, you're going to have a coolant blend that's good for aluminum, and you should do just fine. If you have different machines and different sumps, you want to relegate what materials in what line and make sure that your coolant's proper for that. Um, your fluid specialist should be the one to help you sort through that and make sure that you're using the right fluid, right concentration for the right materials. It makes a difference. Go ahead.
Yeah, I would say, certainly, if you're looking at doing a job, okay, say you're a shop that has a gun drill and you're going to have a majority of your work's going to be in titanium, Inconel, cobalt, chrome, these types of materials. A straight oil or a neat oil, which is ester based, is definitely going to have a performance advantage over one which is not as mineral oil based. So in that regard, yes, the base oil type would definitely help in that regard. So that would be something you may want to consider. Viscosity certainly does play a major role, but that also that is dictated on the size of the drill that you're using. So that's typically, if you're doing smaller holes, certainly you're going to use a thinner viscosity oil. If you're doing larger holes, you're going to want a thicker viscosity oil. But the additive packages is really what's going to be what brings a level of performance to the drill. So you may want a heavily sulfurized oil in addition to having an oil with chlorine in it, with a chlorinated package in it as well. But certainly the different types of base oil can bring a lot to the table. One thing you may want to consider: say you have you're using an oil and you have a lot of foam being generated in that oil. So air is a very poor cooling medium, and you're dealing with an aerated fluid. You're not dealing with a solid fluid anymore, and so your cutting performance is going to uh, diminish. It's going to be sacrificed because of that entrained air. So you may want to use a thinner oil to help release the air faster, or you may want to go to an oil which is gas to liquid based technology, which releases air faster than an ester based oil can or a mineral based oil can, and that actually will help in regards to the cutting performance. So there's a lot of things that go into making an operation successful, and so there's many facets. And unfortunately, the answer to a lot of things, is it depends. So you really need to talk to uh, your 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 vendors who you work with and allow them to help you with these type of issues.
Thank you for answering that question. And it looks like we got another one. And I think I'll be able to show this one on the screen. I'm not sure what this is going to do. Replace load third. Are you guys able to see that?
Mm-hmm.
All right. So yeah, that is the next question.
Like in deep hole drilling, yeah, cryogenic machining that's been tried here and there. There was a study done in conjunction with MAG, Machine Tool Builder, and Lockheed Martin on cryogenic machining of titanium. And typically, the colder you can keep the tool will last quite a bit longer. Um, there's other issues that you have to deal with when you're dealing with cryogenic machining. You're talking with high levels of CO2 being generated. Companies today are trying to reduce their CO2 footprint and the footprint that their facility has in the overall environment. Also, there's you know combinations of cryogenic machining with MQL introduced in through the tool that can certainly work. MQL delivered under high pressure works extremely well. Don't know if it's necessarily the best application though for deep hole drilling, because you really need to have some type of a carrier of a fluid to evacuate the chips out of the hole. So you don't want to be recutting those chips, and you don't want to get chip packing in the flutes. And so, is there benefits to cryogenic machine MQL? Yes, in certain applications. It can be rather expensive. Also, if you're going to do MQL, you have to have the right tooling setup for MQL. You have to have the right delivery, whether it's a single channel or dual channel system for MQL. So there's a lot of things that go into being successful with MQL and cryogenic machining. So, and cryogenic machining is extremely specialized. Um, MQL, most metalworking fluids manufacturers should have decent knowledge on MQL. But cryogenic is extremely specialized, and you don't really see it very often. I've never seen it in the 20 years I've been working at Blaser, and I was a machinist before that. So, yeah, it's
I haven't
a
seen
very
it
special.
outside of being a show special. Yeah. Somebody
Yeah,
try to
I agree.
promote it at IMTS or something like that. That's
Yeah,
about as much as I've ever seen it.
yeah, yeah. I mean, it's cool. I mean, literally, but it's a rather expensive proposition, in my opinion.
All right. Thank you for answering that question. And it seems like that is the last question. So thank you so much to our contributors for presenting today and taking the time to share your technical information and for putting up with all of the glitches that Vimeo has to offer.
All right.
Thank you for everyone who attended today's event. If you wish to reach out to either of today's presenters, their contact information is shown here, and this slideshow webinar is available to download on our website, ctemag.com/webinars, and it's available on this webinars page. And the pre-recorded version of this, or the recorded version of this webinar will also be available on our website to watch back. So thank you for everyone who attended, and have a great rest of your day.
Thank you.
Thank you.